Hello everyone, and welcome back to Kestin Koch, the channel dedicated to demystifying complex technology through design. You interact with artificial intelligence every single day. Think about it. Your phone unlocking with your face, your bank detecting fraud before it happens, or even the perfect song suggestion popping up on your playlist. AI is everywhere. But for something so powerful, the core concept, machine learning, is often overcomplicated. How does this digital brain actually go from zero knowledge to predicting the future? Today, we're breaking it down. We've designed a professional, step-by-step visual blueprint of the AI learning loop. We will show you exactly how data is processed, the role of the neural network, and why the feedback loop is the engine of all modern intelligence. Get ready to see the logic behind the magic. Let's dive into the core of machine learning. To understand the AI learning loop, we start with the foundation, the data. AI cannot learn without massive amounts of information. This is often called big data. Imagine you want an AI to identify a cat. You don't just give it one photo. You give it millions of photos of every type of cat from every angle with labels that say, "This is a cat." This labeled information is the training data. The quality and volume of this data directly determine how smart the AI will be. Now, where does this data go? It feeds directly into the heart of the system, the neural network. The neural network is a mathematical structure inspired by the human brain. It's composed of three layers: input layers, where the data enters; hidden layers, where the calculations and pattern recognition happen; and output layers, where the prediction comes out. Each tiny circle or node in that network processes a small part of the information. The goal is simple: assign a weight to the data to see which features are most important. This is where the magic of finding patterns truly begins. Pass through the neural network's hidden layers, it reaches the final stage, the output layer, which provides the prediction. For instance, the AI confidently states, "Prediction, 95% chance this is a cat." This is the model's first guess. Now we enter the most critical phase, the feedback loop. If the AI guesses correctly, it was indeed a cat, the system reinforces the weights it used. But if the AI is wrong, it predicts a cat, but the picture was a dog, this is an error signal. The algorithm calculates the exact degree of error. This measured error is sent back through the network via the thick, curved feedback loop. The process of sending the error back to adjust the network is called backpropagation. Backpropagation is the AI's way of saying, "I was wrong, let me learn from this mistake." It adjusts the weights and connections in the neural network, making the dog features less likely and the cat features more likely next time. This continuous cycle is why AI models keep improving, even after they are deployed. Now that we understand the core learning loop, it's important to know there are three main types of machine learning models, and each learns differently. 1. Supervised learning. This is the most common form. The AI is trained on labeled data, for example, millions of photos clearly marked cat or dog. The supervisor, the human, tells the AI exactly what the answer should be. This method is incredibly powerful because the model's error is always measurable, allowing for high accuracy. This is excellent for tasks like image recognition, predicting house prices, and classifying spam emails. The key advantage here is precision, but the drawback is the high cost of manually labeling all that data. Unsupervised learning, here the AI receives unlabeled data. The AI must figure out the patterns and structures entirely on its own. It's like giving the model a pile of clothes and asking it to sort them without telling it what colors or sizes are. The result is clustering and dimensionality reduction. For instance, grouping all similar customers together based on their buying habits for targeted advertising, or identifying new, unknown fraud patterns. This is highly valuable for exploration, but the results can be harder to interpret. Reinforcement learning is based purely on rewards and punishments. The AI, often called an agent, learns by interacting with its environment, aiming for a specific long-term goal. If it makes a good move, for example, scoring a point in a video game or successfully navigating a corner in a simulation, it gets a positive reward. If it makes a bad move, it gets a negative punishment. It's the most complex method, requiring millions of simulations, but it's crucial for training autonomous systems like advanced robots and self-driving cars, where the environment is constantly changing. Each method uses the neural network slightly differently, but the underlying principle of continuous self-correction and pattern recognition remains the same, driving all the intelligent systems we see today. So, what's the big takeaway from today's deep dive? Machine learning is not magic. It's a persistent, systematic process of trial and error. It relies entirely on the quality of the training data and the efficiency of the feedback loop. Every successful prediction you see, from a powerful image generation model to a simple spam filter, is the result of the AI making and correcting millions of mistakes in an endless cycle. By visualizing the AI learning loop, we can clearly see that the future of intelligence is really the future of efficient learning. Now, for our challenge, we are dedicated to making complex technology accessible. If you found this visual breakdown helpful, please hit the like button. It helps us reach more people who need simple explanations. And if you want to stay ahead of the curve, don't forget to subscribe and turn on notifications. We are committed to visualizing the next big concept every week, translating the most advanced technical white papers into clear 9-minute videos just like this one. We want your input. Tell us in the comments below, which complex technology should we demystify and visualize next? Should we tackle quantum computing, the metaverse, or perhaps the inner workings of an autonomous vehicle? Your feedback drives the content. Thank you for watching, and we'll see you in the next visual.